misconception is that it involves ionizing radiation. Please be quiet. Thank you. Okay, so it doesn't. The nuclear just refers to a property of the nucleus called spin. Not every nucleus, but certainly the nuclei of protons. Certain isotopes, a rare heavy isotope of carbon, phosphorus 31, fluorine 19, and so on. Now, as you're going to see, NMR gives us very detailed information. And to the point where you can very often determine chemical structure from NMR alone, but certainly using NMR, mass spec, and IR, it becomes really much, much easier to determine organic structures. It's a very powerful tool. This tool has only been with us since the 1950s, so not very long. Makes you wonder how how organic chemists did anything before the advent of NMR. Once you recognize the power of this tool, you really can't imagine living without it. Let's take an overview and just take a look and see what exactly this thing is. So it is spectroscopy. It's not a destructive technique like mass spec. So after you run your NMR sample, you have your sample back. You don't lose anything, okay, which is kind of nice. It's also very, very sensitive these days. You don't need a lot of material. In the old days, you needed really macroscopic amounts of material. You needed, when I started studying chemistry, it was common to run samples on, 50 to 100 milligrams. And anything less than that seemed, you wouldn't get good spectra. Now, routinely, and this happened when I was in graduate school, routinely you can get very good spectra on milligram or sub-milligram quantities of material. And that's really revolutionized the way research gets done and the way drugs are discovered and many other things. So, okay, so overview of proton NMR. So we're going to talk about proton NMR first, because proton NMR is the one that's most useful for us. Most useful for us, proton and then C13. We're probably not going to have a chance to look much at phosphorus. There are a couple of problems I'm going to assign that let you take a look at fluorine NMR, both of which are important, but probably not in the context of this course. So proton and C13 nuclei, but not C12 nuclei, okay, not C12. This has important consequences. Have a property called spin. And so do fluorine 19, phosphorus 31, and some others. Only nuclei that have spin are going to be detectable by NMR. So any nucleus that doesn't have spin is invisible to the NMR spectrum. Okay, so you don't see it at all. Historically, proton NMR was the first we developed, and that's the one we're going to discuss first. Okay, so now what I'd like to do is just jump right in and show you an NMR spectrum. Okay, so this is one I copied from the book. So here's the NMR spectrum of dimethoxymethane. Very simple compound, 2 methoxy groups and CH2. And what you see in this spectrum, you see 2 lines. I'll tell you about this line in a minute. What I want you to notice is that there are 2. Okay, the vertical scale is not going to be important to us. The vertical scale is arbitrary, and you can adjust it just to fit all your peaks. Okay, so don't worry about the vertical scale much. It does have physical significance, as we'll see, but the units are going to be arbitrary. Okay? Now, what you do notice is that you have a frequency scale, and then in parallel, you have another x-axis, which is called chemical shift ppm delta. ppm stands for what? Parts per million. Okay? So these 2 scales are equivalent. The one that we're going to be looking at all the time is this ppm scale. Okay, so we're not going to be reporting peaks in frequencies. We need to know what this is for now, but the real numbers are going to be down here. So what do we see here? Well, we see 2 peaks. One peak for CH2 and one peak for these 2 CH3s, which will both appear here. Okay, these peaks are referenced to 0. The 0 is taken as the peak for TMS. TMS is tetramethyl silane. So TMS is just an additive where you take silicon with 4 methyl groups. You can buy this in little brown bottles. It's cheap. And TMS is this stuff here. it has one kind of proton. All of those methyls are chemically equivalent. And so you see this one peak at 0 parts per million for TMS. Why TMS? Well, because it's practical. It has a boiling point around 26.5 degrees C. So at the end of the experiment, you evaporate it off and your sample is not contaminated with anything. And for reasons that I'm not going to go into right now, that peak appears in a part of the spectrum where few, if any, other things appear. So it's a nice reference. So all these peaks are going to be referenced to TMS. Okay. Now, so what we're going to be looking at is, so that's what the spectrum looks like. So what the spectrum is a plot of energy absorption. Always we're absorbing energy, and we're talking about electromagnetic energy on the y-axis versus frequency. Okay, so we have a frequency x-axis, we have absorption of energy on the y-axis. The y-axis, as I said, had arbitrary units. We're going to see what the physical significance is of that. Now, what I want you to notice is that what I'm repeating myself, that the x-axis is shown in parts per million or delta, same thing, and there's a correspondence with the frequency units. Frequency units are reciprocal hertz, which is reciprocal seconds. That's always going to be the frequency unit that you see in here. And it looks like for every frequency, we have something that's called a ppm, okay? So frequency of the radiation, right? Okay, so most of the spectra are going to be 300 megahertz spectra, okay? And you'll see what that means. So you're going to see that the number of hertz is given by 300 times 1. So 300 times 1, 300. 300 times 2, 600, and so on. 300 times 8, 2400. So there's a one-to-one correspondence here. These are both linear scales, okay? And so the 300 megahertz is the usual spectrometer frequency. We're going to see what that means. So in this department, we have one 300 megahertz NMR spectrometer. We also have a 400 and a 500 megahertz machine. So we have 3 of them. So what I just showed you on that spectrum was that the parts per million, always given by Greek delta, is going to be equal to delta nu. Delta nu is the delta means a difference in frequencies divided by 300. Now, what's this difference of frequencies? Well, the difference of frequency is the difference between the frequency where TMS comes and the frequency of your peak. So 0 minus whatever this is about 1,000 hertz for this one, and the difference here is about 1,360 hertz for the other one. So delta nu is this delta nu. It's that difference in frequency. Difference with respect to what? Well, with respect to TMS, which is your 0 point. Okay, so this is common, right? I mean, if you're going to have a reference, then you measure things relative to that reference, and we're not doing anything unusual there. We're just using the reference of 0 as the start point, reference for TMS. Okay, now 1 megahertz is 10 to the 6th hertz, right? Mega is the prefix that indicates a million. So 1 megahertz has a million hertz in it. And now you can kind of see where this parts per million comes from. I said that the units on the x-axis were delta or parts per million. What did the parts per million of what? Well, it's parts per million because I have a numerator of hertz and a denominator of megahertz. So this gives you something that is a part per million, right? So we measure the difference in frequency in hertz over the spectrometer frequency, which is 300 million hertz, so parts per million. Okay, now there's a reason why we do this. You say that, oh gee, why complicate things? Why do we have to have parts per million? Why don't we just measure everything in hertz and then it becomes easier to understand? Well, not necessarily, and you're going to see why. Now, the peaks that you see in the NMR spectrum, we're going to call these, and I'm not going to be consistent, I'm going to call them peaks or lines or absorptions or whatever. It all means the same thing. It's those lines in the spectrum that you see. Now, the way I showed the spectrum, because it is extremely high resolution, this looks like a line. Actually, it's not. It's got width to it, okay? And so if this spectrum were taken at a lower resolution, you'd see kind of a triangle here. You'd see kind of a peak, but you don't see that because this is very well resolved, okay? The peak position, in this case, this is about 3.4 delta parts per million, and this is about 4.6 parts per million. These are going to be called chemical shifts. Okay, so the chemical shift here is about 3.4. This one is whatever. So we need to learn a little bit of this peak speed so we understand what we're talking about. Now, almost always, those peaks are going to be referenced to the zero of TMS, of tetramethylsilane. And by definition, and this is just defined, right? By definition, TMS appears at 0 ppm. So whenever you see a TMS peak, 0. You don't have to think about it. Why? That's just the definition. We define that as our 0. That's what it means to have a reference. Okay. Now, for the spectrum that I showed you, I want you to notice that you have two peaks. Two different peaks because why? Because in that molecule, you only have two different kinds of chemically non-equivalent protons. Okay, so this is important. Every chemically non-equivalent proton potentially gives you a separate peak. Now, why do I say potentially? Well, potentially because why? Well, because, yeah, you could have chemically distinct protons, but the difference in their absorption are tiny, tiny, tiny. And so even though, yes, they are different, you can't really tell because they're right on top of each other or almost on top of each other. So that can happen. However, whenever you have chemically non-equivalent protons, you will have distinct peaks in the NMR, except if they overlap accidentally, which can happen. Now, that's one thing. The second thing I want you to notice is the peak heights. Notice that I have two different peak heights. This was the CH2. This is for the two CH3s. The ratio of the peak heights is in the ratio of these protons. So it's going to be 2 to 6, or if you will, 1 to 3. And it's actually not the peak heights that you're looking at the ratio of. You're looking at the area under the peaks. I said that these look like lines, but actually no, they do have area under there. It's just they're very narrow lines, very narrow peaks. So the area under each of these peaks, or more precisely the ratio of the areas under these peaks, correspond to the ratio of the protons. Now, you don't know the absolute numbers of protons, right? The NMR is not going to tell you, oh, I got 2 here and 6 there. It could be 1 to 3. But it will give you the precise ratio. Okay? So here it is. So the ratio of the absorptions are proportional to the numbers of protons that are responsible for, in this case, 2 to 6. But the absolute numbers, you don't know. Just the ratio. Well, you can say, how useful is that? That turns out to be really useful because you can almost always piece together what you have from that ratio. Now, the other thing I want you to notice is the two lines, or two peaks in that spectrum, don't appear at the same frequency. So they don't appear at the same chemical shift. Chemical shifts of the CH2 are appreciably different from the chemical shift for the methyls. In fact, they're separated by a mile. And you'll notice that the CH2 appears at what? At higher frequency than for the CH3. Now that turns out to be very important. And it's going to give us a lot of information about the chemical environment of the protons that are responsible for that peak. So the high frequency peak, that's the one to the left of the spectrum, was for the CH2. And that CH2 group is flanked by 2 electron withdrawing oxygen atoms. Remember that oxygen is electronegative with respect to carbon. And so the fact that CH2 has 2 oxygens sucking electron density away from it, and that the methoxys only have 1 carbon atom sucking electron density away from it, shows up in the NMR spectrum. The one that has the 2 oxygens pulling away electron density is here, that's this one. The methyls, only 1 oxygen there. that is a difference of about 1 ppm, 1 part per million. That's a huge difference. And the reason is because of the effect, and we're going to see what this is, of those electronegative oxygen atoms. So now it looks as if we get a lot of information from the NMR spectrum. First piece of information you get is the one that we just said, chemical environment of the hydrogens. So depending on what kind of chemical environment, what does chemical environment mean? Well, it means, does it have an oxygen on the carbon? Is there fluorine? Is there a double bond? Is there, you're going to see that has a big effect on the chemical shift. So we can tell something important about the chemical environment from, you can tell the ratio of the number of protons within each set of chemically equivalent protons. And then something that you can't see in this spectrum, but that's going to be very important, is the number of protons on the adjacent carbon atom. And so here, you don't have an adjacent carbon atom, right? You have carbon-oxygen-carbon. You don't have carbon-carbon. But if you have carbon and carbon, then from this peak, you'll be able to tell that there are two hydrogens on the neighboring carbon. And from whatever absorption these two have, you'll be able to tell that there's only one hydrogen on the adjacent carbon atom. And so these three pieces of information make it possible, just from proton NMR, I'm not even talking about C13 NMR yet, just from proton NMR, these three pieces of information can allow you to determine structure very often. Okay? So this gives you a very, very powerful tool. Notice that this is very different from any of the other spectroscopies that we've seen so far. UV just tells you about the conjugated double bonds in the system. It doesn't tell you much at all. IR tells you about functional groups. Mass spec, not spectroscopy, I know, it tells you molecular weight and fragments. It gives you a lot of information, but not detailed like this. So this gives you the real information. It's almost like a photograph of the molecule. Okay, so this is the experiment. Now, this is the way, the kind of information. How do you get this information? In other words, what's the physical basis for all of this? So, electrons and protons and C13 nuclei and a few others have this property called spin. And for electrons and for protons, there are only two spin states, +1/2 and -1/2. These are quantum numbers. Don't worry too much about what that means. Just know that there are two spin states for proton. And the fact that a nucleus has spin means that it acts like a small magnet. Okay, so it has a magnetization. And so let's just say that you have a flask with a molecule that has protons. Let's forget about what the molecule is. Just focus on each proton. Each one of those protons is going to have either a +1/2 or -1/2 spin. And these spins are going to be oriented randomly. Okay, so I tried to show that with these vectors. So you're going to have some kind of random orientation of each of the spins. But if you apply a very strong magnetic field to your sample, then all of a sudden what happens is these spins line up, like little bar magnets. So if you put a needle inside a magnetic field, the needle will move around. It'll align with the lines of magnetic force. And same thing happens here with nuclei. So if I have my sample and I put it in the region of inside a very strong magnet, then all of a sudden those random spins flip up or down. Now you could say that they can either align with the field, so if this is the direction of the field, they can either align, so they're parallel, or they can be anti-parallel. It turns out the spin +1/2 are parallel and spin -1/2 are anti-parallel. There's a small difference in energy between these two. Now, this difference in energy is the one that the NMR experiment is going to measure. Okay? And so the way you measure that is by the normal way. You add electromagnetic radiation, and then you see what gets absorbed. The only difference with the NMR is that, unlike the other kinds of spectroscopies, UV and IR, here, in order to see that absorption and energy, you have to apply a magnetic field. And so the difference is that, for UV, for IR, you just do those in the absence of a magnetic field. Here, you need a really strong magnetic field. And so after you apply an external magnetic field, then the spin states, the +1/2 and -1/2, these have different energies. That's what I tried to show you. But the energy difference is really small. And it's given by the fundamental equation of NMR. So this is one that you kind of need to remember. The energy of the difference in energy of the protons is given by Planck's constant over 2 pi. So this part is constant. This gamma sub h is a constant in nature. That's a number that is associated with each NMR active nucleus. So for protons, there's going to be 1 gamma sub h. For carbons, there's going to be a gamma sub c. For fluorine, a gamma sub f, and so on. These numbers are going to be different, but they are constant for each nucleus. And so this whole business is constant. Okay, so for protons, this is a constant. B sub p is going to be the strength of a magnetic field. And it's the magnetic field that the proton experiences. And this is going to be critical. Okay? Now, I noticed 2 things. I noticed a few people walking out. And I also noticed that I don't have a full classroom here. I hope the people who walked out and the people who didn't show up today are planning on dropping this course. Because guess what? By not paying attention to this particular lecture, you're really setting yourself up for failure. So this stuff is not easy. I know it isn't. But you don't listen to it, or you don't hear it, you don't think about it, you're not going to learn it. And it's going to come back on every exam, okay? So you know. Okay, so let's go through this again. Fundamental equation of NMR. Difference in energy between the 2 spin states is given by this constant times the field strength. So notice that the energy in the magnetic field are proportional to each other. Big field, big difference in energy. Tiny field, small difference in energy. Now, what does that tell you? It tells you that because big differences in energy are a lot easier to measure accurately than little tiny differences in energy. What it tells you is that if you want to record a good NMR spectrum, what you want is the biggest, baddest magnet you can get. Why is that? Well, because the strongest field will give you the best separation in energy between the spin states, making the experiment easier to perform. That's not easy to do. I mean, it sounds easy. It's not. So let's take a look at the constants here. So Planck's constant we've seen. I've given it in kilojoules per second per mole. The gamma, this is called the gyromagnetic ratio. Sometimes you'll see it magnetogyric ratio, but you know it's the same thing. This is just a fundamental constant. Don't worry about what it means right now. Just know that it's a constant for proton. It's a different constant for C13 and so on. For protons, it turns out to be this number, which is fairly big, 26,700. Now, going back to the equation, you can see that this gamma is going to be important, right? Because, look, if this is a really small number, then it means that to get a big difference in energy, you're going to need a much bigger magnetic field. So if this is a big number, then a smaller magnetic field will translate into a larger energy difference. So for protons, we're lucky. Why are we lucky? Well, because gamma is a pretty big number, which means that even a modest magnet can give you large energy separation, so you can do the NMR experiment quite easily. So this is a fundamental constant for each nucleus. And then B sub p is the strength of the applied magnetic field at the proton. Okay, now this is going to become very, very important. Okay, so we're not talking about just the applied field. We're talking about the field that proton experiences, and those are not going to be the same. Okay, so we'll make a big deal of this in a bit. Okay, now I give you these numbers. You can at home you can take out your calculators and multiply things out. And you find that if I take a typical magnetic field of 78,500 Gauss, Gauss is the unit that's used to measure a magnetic field. It turns out to be a really strong magnet, by the way. You can't buy these in the hardware store. If you have a strong magnet like that, and you multiply it out, you notice that the energy in the difference in energy between the two spin states or proton is this tiny number. This is a really small number. So this is a hard experiment to do because you're looking at really infinitesimal differences in energy. Your book has you do something kind of nice actually. It tells you that take that difference in energy, which is this much, and remember that difference in energy is related to log k equilibrium. If you multiply this out and take the antilog and whatnot, you find the k equilibrium for this tiny bit of energy is almost 1. Holy smokes, what does that mean? Well, it means that you have such a small excess of nuclei in the high energy level. So that also tells you that it's a small energy level, small number of nuclei in the high energy state. It's going to be hard to measure anything. So, how do you get this bigger? Well, you know. You know how to get it bigger because you know that everything in this equation is a constant except for that. So if I want to make this big, I've got to make that big. So if I want to make a big energy difference between the nuclei, I need a strong magnetic field. So the only way to increase the energy separation between plus and minus 1/2 spins is to increase V sub p. So what this shows is energy versus energy separation for the minus and the plus 1/2 spins as V sub p increases. So if I have zero magnetic field, plus 1/2 and minus 1/2 spins are going to have identical energies. Nothing to measure. But as the magnetic field increases, the energy separation between minus and plus increases. So if I go out here, then the energy difference will be even bigger. So if there's zero magnetic field, then the difference in energy is going to be 0. But you knew that anyway from the equation. Okay, so now let's talk about. So now we know. Okay, so what have we talked about so far? We just said that nuclei. And when I say nuclei now, I'm just going to talk about protons. Okay, so protons have this property called spin. And so that spin can have one of two states, either plus 1/2, minus 1/2. In the absence of a magnetic field, both of those spins have identical energy. I put the protons in a strong magnetic field. Now all of a sudden, the minus 1/2 spin protons are a little bit higher in energy than the plus 1/2. Not much, very little bit. But that doesn't tell us how we're going to do the measurement. So let's take a look. Now, the measurement, as I said, is going to be difficult because K equilibrium for even in a strong magnetic field, a 70,000 Gauss field, K equilibrium is almost 1. It's tiny little excess, right? So it turns out that if you crunch the numbers, it turns out if you have 1 million, high energy spins, there's only 1 million plus 20 low energy spins. Oh, not much. That's a challenging experiment. Now, how do we do the experiment? Well, let's take a look. So here we are with the applied magnetic field. I have a few more low energy spins than high energy spins. And now I do the same thing I always do. I shine electromagnetic radiation on the sample. And so the frequency of the electromagnetic radiation is going to have to match the energy difference between these two spins. And if I do that, then a few of the plus 1/2 nuclei, the low energy ones, will absorb energy and they'll become minus 1/2 spins. So a few of these will go up here and become green and be aligned anti-parallel with the field. So I shine electromagnetic radiation on this. A few of these low energy ones come up here and become high energy ones. This is known as a spin flip. Okay, so these spins flip over. And in so doing, they absorb energy. So in order for that spin to go from plus 1/2 to minus 1/2, it has to suck up a little bit of energy. Where does that energy come from? Well, it comes from the RF coil that surrounds the sample, that gives it a little bit of electromagnetic radiation of the right frequency so it can absorb energy. The absorption of that energy is what you measure. So you're measuring a small number of nuclei absorbing a tiny amount of energy. Okay? And that's the experiment. Now, one thing, we say nuclear magnetic resonance. Don't confuse resonance structures with nuclear magnetic resonance, okay? Two completely different things. Now, to recap, it's not any different from any other spectroscopy. You have a sample, you shine electromagnetic radiation on it, it absorbs a little bit of it, you measure what's absorbed, and the absorption versus frequency gives you the spectrum. Same here. The only difference, here there's a magnetic field. Why is there a magnetic field? Well, because if you don't have that magnetic field, then the energies of those two spin states are identical, and there's nothing to measure. So in order to measure a difference in energy, you have to put them into a strong magnetic field, so plus 1/2 and minus 1/2 spins are separated by some energy. Stronger the magnet, the bigger the energy separation. Okay, now the frequency. Okay, so I said something about RF coils, and I didn't explain that at all. It's explained in the text, but we'll talk about it. So the difference in energy between plus and 1/2 and minus 1/2 is given by the same equation that we've seen before. Planck's constant times frequency. So high frequency, high energy, yada yada. Okay? And so H nu is going to be equal to all of this. This, remember, was the fundamental NMR equation. But the H's can cancel. And so the frequency of the radiation is given by this. And you'll notice that once again, frequency, not surprising because frequency is proportional to energy, frequency is also proportional to the magnetic field. So the frequency of the radiation that's absorbed by the plus 1/2 nuclei to undergo spin flip is going to be proportional to the applied magnetic field. So that's what this equation tells you. And then, since I know what these numbers are, this was, remember, 70,000 Gauss, 7,500 Gauss, I can multiply this all out, and I come up with this many hertz, or roughly 300 megahertz. So remember I said we had 300 megahertz machines? What that really means is that we have a machine that has a magnet of 70,500 Gauss. Okay? So whether I talk about megahertz in terms of the frequency, or if I talk about field strength, I'm talking about exactly the same thing. Now, as it turns out, this frequency, that frequency, is in the FM and ham radio signal range. So what you have, I said an RF coil, what you have is a little radio transmitter, okay? And so you're absorbing energy that's in the radio waves region of the spectrum. And so kind of an elegant experiment. You have a strong magnetic field. You shine appropriate radiation in this region of the electromagnetic spectrum. Absorb a tiny bit of energy. You measure that. You get a signal. Now, not all magnets are going to have the same field strength, which means what? If they don't have all the same field strength, then the frequency here is not going to be the same, the frequency of the radiation. And so that creates a problem. Creates a problem because, look, I have a really strong magnet. I measure spectra for the same compound that you measure using a really weak magnet. Now we want to compare our results. And if we report them in hertz, then, hey, guess what? We're going to have different results because, you're going to measure a smaller number of hertz because you have a weaker magnet, and I have a stronger magnet. I'm going to measure a larger number of hertz, and we can't talk to each other. And so the reason we do this parts per million business is to cancel everything out. So the reason that you have this parts per million, we're going to go through this again, is so that regardless of magnet strength, the peak position is going to be identical when measured in delta units or ppm. Okay? So that's why we went through that whole rigmarole. So not all magnets are the same field strength, and the frequency is going to be proportional to the field strength. Now, just as a historical note, the NMR phenomenon was discovered independently by Felix Bloch and Purcell. Bloch was at Stanford, Purcell was at Harvard, just about the same time. These are physicists, and they were not, they weren't interested in chemical structure. And so it took a little bit of time for the chemists to get on board and realize that, hey, this thing actually has some value. So we're going to see now how, what the nuts and bolts look like. So I'm going to repeat myself a few times here because I know this stuff is new to you and it's a little bit hard to absorb. So going back to what we said, if I apply a magnetic field to these 1/2, -1/2, +1/2 spins, the energy separation is going to be proportional to the field strength. So if I have zero field, those spins are identical energies, nothing to measure. So I have to have a strong magnet, the stronger the better, so that I have a big, big energy separation. So our discussion, however, so far would indicate that all protons, regardless, should have that same energy separation for a given field. And if the energy separation is the same for all the protons, then all of those protons should absorb at exactly the same frequency, which means that when I run an NMR spectrum, I shouldn't see this. I should see one peak for all of them. I should just see one peak, but I don't. I see two peaks. And so there's got to be more to this equation, because what this implies is that for any given field strength, this is the energy separation. But remember what I said about the field. It's not the applied magnetic field. It's the field experienced by each proton, and it's not the same. So here's what you want to think about. I have a magnet, strong magnet. Sure, that gives you 70,500 Gauss. But where I measure at the proton, that 70,500 Gauss is not 70,500. It's either a little bit more or a little bit less. Why should it be different? I mean, heck, I applied that magnetic field. What made it change? What made it change were the bonding electrons, okay? And so depending on the chemical environment, you induce a magnetic field in the region near the proton that either augments the applied field or subtracts from it. That little bit of change in the magnetic field over the applied, it depends on the chemical environment, it depends on the electrons, that little bit of change, that is what leads to the difference in the separation in peaks. And that's why it's important, and that's why it's useful. Because if that didn't happen, then all protons and all molecules would all have the same line no matter what. You get zero information. But the reason you get information is because you have differences in the local magnetic field of each proton depending on the chemical environment. So the applied field and the local field that the proton experiences, they're not the same. If they were the same, it would be useless. But you already knew this because I told you. Remember, I said that this compound had two lines because electrons were throwing oxygen and all that. Okay? So I already told you this. So what I just mentioned now is sort of repetition. So we can't vary Planck's constant, we can't vary pi, gamma sub h given to us by nature. This is given to us by the spectrometer. And so what varies, however, is the local field. And so what that means is that the magnetic field that these methyl groups experience cannot be the same as the magnetic field that those CH2 groups experience. Why can I say that? Well, because if it was, I wouldn't see the two peaks. I'd see one peak, but I see two. And the fact that I see two tells me that since all of this is a constant, that was the only thing that could have changed. And so somehow the energy separation for spin flip here and the energy separation for spin flip there are different. Why? Because the local field is not the same. That V sub P, that sub P means at the proton. So for this proton, it's a different field. For that proton, it's a different field. So the local magnetic field experienced by CH3 and CH2 is not the same. If it was the same, you'd see one peak. You don't see two peaks. Okay, so now let's think a little bit about what's going on here. So you already know that they don't experience the same field. Okay, but why? Why should the field be different for one and different from the other? Well, here's the general thing that I want you to remember. If you have electrons, those electrons can respond to the applied field, and they can induce typically another field that is opposed to the applied one. Okay, now sometimes not opposed, sometimes it augments it. We'll see why. But most of the time, the applied magnetic field will generate another very small magnetic field in the vicinity of the proton that opposes the applied magnetic field. Most of the time it opposes. As I said, so we're going to see an example, or we'll see examples where it augments it too, but most of the time it opposes. This is called shielding. So if I look at protons here, the ones that are over to this side are shielded. So these will be shielded. Anything that's out here is de-shielded. Shielded on the right-hand side, de-shielded there. You're going to see why that makes sense. So just to recap, nearby electrons can shield the proton from the applied magnetic field. So if I have high electron density near the proton that I'm looking at, that proton is going to require a stronger magnetic field it's going to require a higher frequency to come into resonance. And so from the spectrum, you can see that this CH2 absorbs, comes into resonance, means the same thing, absorbs at higher frequency than the metals. So the frequency, remember, increases to the left. So let's take a look here. So delta nu here, remember, was, 1368. Here it's about 1005. So CH2 requires higher frequency. If it requires higher frequency, what does that mean? Well, it means that the energy separation of the two states, the two spin states, is greater. So greater energy separation here, smaller energy separation there. If this is a greater energy separation, then what does that tell me about the magnetic field? If it's a greater energy separation, it means the field's stronger. So what that means is that the field experienced by these CH2s is greater than the field experienced by these metals. Now, why should that be? Well, because these CH2s are de-shielded by the electronegative oxygen atoms. So electronegative oxygen atoms pull away electron density from that CH2. No electrons, no shielding. That's it. Simple. So all of this is simple, but putting it together is not. That's why you need to kind of think about this stuff. So these are going to be de-shielded relative to that. Why? Because I have two electronegative oxygens pulling electrons away. The presence of those electrons would have shielded the CH2. They're not there. Why aren't they there? Because oxygen is electronegative. And so what I showed you from the spectrum was that the frequency for the CH2 absorption is going to be greater than for CH3. That means, and so if I take the relative frequency, I just take the TMS peak frequency and I subtract it out. So I just subtract the frequency of the TMS from each side. Haven't changed anything. And what that means is that the delta news, I mean, just doing the arithmetic here, this is just the same, saying the same thing. If I divide this by the spectrometer frequency, then what I end up with is these two frequencies divided by 300 gives me the peak positions for CH2 and CH3 in parts per million. And so now you can see, once again, why it is that we want this parts per million business. Because by dividing these frequencies by the spectrometer frequency, we cancel out any differences due to magnetic field differences from your machine and mine. And so the CH2 is going to be absorbing at exactly the same position, whether it's in 300 megahertz or 600 megahertz, because this number will change, but this will not. So ppms will not change regardless of what that is, regardless of what the spectrometer frequency is. So that's why we bother with this ppm business. Okay, so I think this is the end of our. We'll pick up on Friday. Okay?